At the top of the screen, there is a mirror, and it has a fascinating property. The light beam is always reflected back to the middle of the table. All kinds of things exploit that property, from electric fires to radio telescopes. But is that the only reflector that will do the job? Let's take the lights down and have a look at this. Here's our original reflector. But what about this one? That does it too. So does this. In fact, there is an infinite number of reflectors of different shape that all have a common property. They all focus this light beam onto this point. We say that all those reflectors form a family. Now, if I wanted to design such a reflector for a particular purpose, then I would want the equation for every one of those curves in order to pick the best one for the particular job. So, how do I get those equations? Our hunt for those equations will lead us through many of the elementary properties of differential equations. But let's start with a physical attack on the problem. We want to find how the curves reflect light at every point on the table. So let's start out by looking at the reflection of a single beam at a single point, which I can do with this small mirror. There is a specific direction at which I must set this mirror in order to reflect the beam back to this point. But that's only just one point. Now let's examine reflections at a sample of points on the table. Only when the mirror is set in this direction does the beam hit the origin. At the point above, the same angle doesn't work. We need a different direction. Another point. And another direction. At each point, there is a unique angle or direction for setting the mirror. In this way, the mirror builds up a whole set of directions. And so at every point, we have a specific direction or angle for setting the mirror. And in principle, a mirror will give us the direction at any point. That will reflect the beam back to the center. This is only a sample of possible directions. But the association of a direction with each point establishes what is called a direction field. So what have we done? We've got a whole field of directions. But we started out looking for the equations of these curves. What's the relationship between the field of directions and the family of curves? Here's the direction field, and now the family of curves. There's a striking visual resemblance. See how the curves fit the direction field? The slope of each curve matching the direction in the direction field. We've done all this physically, using mirrors. And from the direction field, you could have a go sketching any one of the reflector curves without even doing any mathematics. But what we really want are the equations of the curves. We want to make a mathematical connection between a direction field and a family of curves.
Now, if you want to find a mathematical connection, we should define our direction field mathematically. So, for the moment, instead of the reflector problem with a physical direction field, we'll choose a mathematical problem. It's a good idea to start with something simple. So let's take this problem, where the slope is equal to minus x over y. And this certainly defines the slope at any point. For example, if we take this point, shall we say, that's the point 7, 3. And therefore the slope will be minus 7 over 3. It will be something like that. Now, what about the point 3, 3? That's that one. So the slope there will be minus 1. Something like that. And the same thing for 5, 5. That will be minus 1 as well. So that's a few points. But to get a better idea of the direction field, we'll need slopes at many more points. Well, we've got a formula, and that's just right for a computer. When x equals y, the slopes are minus 1. When x is minus y, the slopes are plus 1. Other values will just give intermediate slopes. Well, that's the direction field. And now we've got to find some curves that fit. Well, what curves do you think would fit this? I would sketch something in like this. And perhaps another curve, something like this. Well, they look like circles, but these are only drawn by hand. So let's get a computer to draw some circles to see how good the fit really is. Circles seem to fit pretty well. How can we check that? Take a closer look. Notice how the directions form tangents to the circle. And it's because they all form tangents that from this direction field we get a family of circles. And that's something we can show analytically. We can check that the tangents of the circles belong to this direction field. Well, we know what the equation of a circle is. It's that. And now we have to turn that round to turn it into a function. And that will be y equals and we'll put the positive square root so as we check the upper half of the plane. Now, we have to differentiate that to get tangents. And I hope you've got the same answer as I did. That is, and that is merely equal to minus x over y. So, for any point on these circles, the tangent has the same slope as the slope defined by the direction field at that point. That proves that circles fit the direction field. In general, the connection between a direction field and a family of curves is that the tangent to each curve exactly matches the slopes in the direction field at that point.
What John had was a mathematical formula for his direction field, and that allowed him to draw in slopes, sketch in curves that seemed to fit, guess the equations for the curves, and then check his guess by differentiating the equations. Can I do the same? Well, first I need a mathematical expression for these slopes. We pick a point, xy. We're looking for the direction of a mirror at xy that reflects light to the origin. Now this direction forms the hypotenuse of a triangle. And the triangle helps us find the slope we're after. It's the vertical height divided by the horizontal. Some of these lengths we know. The point is xy, so the horizontal is just x. Part of the vertical is just y. What's this other length? This length we find from the geometry of another triangle. We have some equal angles from parallel lines and from the laws of reflection. So the triangle is isosceles. The length of one side is the distance from the origin to xy. And an isosceles triangle has two equal sides. And this gives us the other part of the vertical. So the slope we're after is the vertical length divided by the horizontal. We now have a formula for the slope of a direction at any point in the direction field. But what else did John do? He guessed the equations of the curves and found that the slopes of the curves match the direction field. But with my direction field, I don't think I can guess. I'm looking for a way of deducing the equation. So let's go back to the reflectors. We want the equation of a curve. That means I'm looking for a function of x. Now what do I know about the function? The derivative of the function gives the slope of the curve. But the mathematical form of the slope is just what we've established. And now I must put them together. And putting them together gives a new form of equation. It's called a differential equation. Instead of simply connecting the variables x and y, this equation connects the derivative, dy by dx, with the variables y and x. Now, a solution to this differential equation is any function that relates values of y and values of x in a way that satisfies this relationship. Now, I want to use this relationship to find the family of curves of my reflector problem. So, how do I go from the statement of the equation to the family of functions that are its solutions?
Before we continue with Paul's equation, let's look at something simpler to get the main ideas. Here's a differential equation, which tells me that the slope of a solution at any point is simply x. Now, so far we've plotted slopes to get a direction field, and from this guess the curves. But this differential equation is sufficiently simple to get here directly and analytically. Integrating both sides, we get that. And c is the constant of integration. The question is now, how does this represent the family of curves, and how does this agree with the direction field? Let's start with the direction field. When x equals 0, the slopes are 0. They only depend on x. When x is positive, the slopes are positive. And as x increases, the slopes increase. For negative x, negative slopes. That's a sample from the direction field. But if dy dx equals x, then y equals a half x squared plus c. When c is 0, the curve is just a half x squared. For a positive value of c, and this is when c is negative. And c takes different values, so we get the different members of the family. It's this constant c that gives different curves in the family. And do you remember where it came from? It came from integration. What's more, each of these functions is a solution to the differential equation because the derivative of this function satisfies this constraint. But unfortunately, differential equations are not always as simple as this. If we take a problem from the unit, you'll see what I mean. Here, dy dx equals x plus y. And that's more difficult, because we can't integrate it directly. That's because of this y. However, the methods you'll find in the unit boil down to juggling with this until you can integrate it, and juggling a bit more to get an equation for y. You'll see that the answer for this differential equation turns out to be this one. And this will represent the family of curves. Now, two things about c. First, that it comes from integration. And secondly, instead of being just added on, it is firmly embedded in the equation. That's because of the juggling needed by the method. That's the mathematical expression for the solution. Now let's look at a family of curves it describes and see how this family matches the direction field given by x plus y. At points where x equals minus y, x plus y is 0, and the slope is 0. As x increases, so does the slope. And as y decreases, the slope will decrease too. That's the direction field. What curves fit this field? There's one you can see straight away. It's a straight line minus x minus 1. The curve for c equals 0. If c is positive, we'll be adding a multiple of e to the x. For negative values of c, we'll be subtracting e to the x. And so, for each value of c, we get a curve in the family. Isn't that lovely? We just had to show you how a simple differential equation like this could produce a whole lot of curves, all waving about. And yet, all that is controlled by the one constant c. What's more, the curves and the direction field fit together. And so they should. They came from the same differential equation. What we've done illustrates two approaches to differential equations. Sometimes we can get solutions, equations like this, by analytic methods, which involve integration and give the constant c. Alternatively, we can plot the direction field to get a feel for the solution. And of course, in those cases where you can't get an analytic solution, the direction field will lead to approximate solutions.
I'd like an analytical method based on integration, so I'll have to juggle this equation until I can integrate it. Now, it takes a little doing, but it's worked out in the text, and here's the solution. I hope you've checked in your pre-program work that this equation satisfies this relationship. Now, it's obvious that y equal to something times x squared is going to give parabolas. But what I want you to notice is the placement of the constant c. It appears twice. As the add-on term, it shifts the height of the curves, while in the x squared term, it changes the shape. So the constant c changes the curve's shape as it changes its height, as we'd expect from the reflector problem. But let's see that on a computer. This is the curve for one value of c. For a smaller value, and a larger value gives this curve. And there you have it, an equation that can give you every parabolic reflector that does the job. But don't forget the direction field. These curves must fit the direction field, all of them. So that's how we arrived at those actual reflectors. But in this hunt for equations, there are four main points that I want you to remember. First, a direction field specifies a slope at any point xy. Secondly, if you're looking for a curve that will smoothly fit the directions, you can relate values of x and y by a function. And then the slope of the curve becomes dy by dx. Now, in that case, you have a relation between the derivative, dy by dx, and y and x. And this is a differential equation. Any function that relates values of x and y in a way that satisfies this relationship is a solution to the differential equation. And in general, there will be infinitely many different functions that satisfy the same differential equation. Thirdly, you can sometimes get the family of solutions analytically, using integration. Then, the constant of integration will serve to identify or label each member of the family. And finally, the direction field provides a pictorial way of representing the differential equation, which comes in handy if you want to sketch the solution curves without integrating. Integrating differential equations will give the family of solution curves precisely. But the direction field is fundamental. In a sense, the direction field defines these curves. So even if you can't integrate the differential equation, you've always got the direction field. And whether you use it to sketch the curves or to determine the functions analytically, it provides a route to the solutions you're after.